let's jump back into chapter 8 then. So we're working on metric spaces now, general metric spaces. And one of the big important topics is compactness. So probably today we'll talk a bit about general things. What does compactness mean in a metric space? What does it look like? And then I think on Thursday we'll focus in on a particular metric space of the continuous functions on a closed bounded interval and do some more practical examples and look at what does compactness look like in this realistic looking space. So we've looked at compact sets in Rn. So what do we know about compactness in Rn? Yeah.
There are two things.
Okay, what are the two things?
First was Heine-Borel theorem.
The Heine-Borel theorem. Okay, so the Heine-Borel theorem applied. It was actually equivalent. So compactness was equivalent to having the Heine-Borel property. And what else?
Closed and bounded.
Closed and bounded. So that's how we actually define compactness in Rn. So compact in Rn was equivalent to being closed and bounded. And in Rn, either of these would make a perfectly good definition of compactness because they're all completely equivalent to each other. Now, we're sitting in a more general metric space, and we need to come up with a way to define compactness in a way that gives us useful properties right off the bat. So we know that, this is easier to understand, of course. This we actually used to prove something about convergence of subsequences. And so, this is easier to understand. This was actually kind of more useful characterization for proving the kind of things that we really are most interested in practice. So I'm going to start here with the Heine-Borel property and use that as my definition of compactness, and then we'll see what we can infer from there. Okay, so in a metric space, we say that a set is compact if it has the Heine-Borel property. Okay, let's just remind ourselves what that means. It's been a few weeks. All right, so this isn't new information. I'm just going to remind you of it because we're going to use it today. The Heine-Borel property works with the concept of an open covering. Okay, so we said that a collection H of open sets is an open covering for another set. Let's call it T. If when we take the union of all of these open sets, the union contains everything in T. So if T is a subset of the union of all of the H's, such that H is in our covering. Right, this could be a finite union. This could be an infinite collection of sets. It could be countably infinite. It could be uncountably infinite. Or I'm not specifying anything like that. I'm just saying I've got a bunch of open sets. But then the Heine-Borel property said that, well, if T satisfies the Heine-Borel property, then you give me any collection, any open covering you like, which again, it could be uncountably infinite, for all I care. No matter how big it is, I can extract finitely many of those and it's good enough. Okay, so we're going to say that if T is compact and H is any open covering, then we can find a finite collection so a finite collection, call it H1 to HK, oops, HK of these sets, okay, such that T is contained in the union of this finite collection now. Okay, so this is how we're going to start by defining compactness. I'm going to make sure we have the language to talk about closed and bounded as well in a general metric space. All right, we already know what a closed set is. What's a closed set?
It's complement.
Its complement is open. We've already talked about how we build up open neighborhoods in a metric space. So, and we did some examples of how we check if a set is open or closed. Okay, so we know what a closed set is. So T is closed if T complement is open. T is also closed if it contains all its limit points. Okay, then we also have to define boundedness. Bounded, we're going to define once again the diameter of a set, right? The diameter of a set is just going to be the biggest possible distance between points in a set. Okay, so we're going to say that the diameter of T is, okay, we look at the distance between all possible points in our set, so the distance is given by the metric. And then we take the supremum of all those. Okay, and we're going to say that a set is bounded if it has a finite diameter. Okay, so for example, if I take this set of real numbers and I use the discrete metric here, all right, is this closed? You're nodding? Why is it closed?
Because the diameter is never going to be like greater than 1.
Okay, that's boundedness. Is it closed though?
Oh, sorry.
Okay, so the answer to the second question is it bounded? Yeah, the reals are bounded under this metric, right? So the metric matters when we're talking about boundedness. Okay, so we'll put that here. This is bounded since the maximum possible distance between anything, d of t equals 1, which is certainly finite. Is it closed? Yeah.
I think I remember when we explained that the set of water numbers was supposed to open and close.
Right, so we did that with the usual Euclidean metric, I guess, that the set of real numbers was both open and closed. What about in this metric? Well, what do I have to check, I guess? The complement. All right, so what's the complement? It's the null set, all right? Is the empty set open? The empty set is, yes, it's both. It's certainly open, right? Because, well, every point in this set passes the test it needs to pass. Trivially, there was nothing to check, but it does. So this is open. So indeed, the reals are closed under this metric. Okay, so this is an example of a set that's closed and bounded, but of course, the metric matters for these things, right? You know, with the typical Euclidean metric, this would certainly not be a bounded set. Okay, so right away, we start to see that the concepts we have over here, it matters a lot what metric we're working with. And that maybe shouldn't surprise you too much because we've already seen that a concept of what makes an open set, what is the boundary of a set, all of these things depend strongly on the metric that we've chosen. So, okay, so let us now state the main theorem that we kind of care about here. It has to do with extracting convergent subsequences, because as applied mathematicians, that's what we always care about, is we build sequences through some kind of iterative process, and we'd like to know, does it converge? So here our result is that if T is a compact set in a metric space, okay, and we take a sequence in here. Okay, then we can find a convergent subsequence. Xn itself may not converge. A general sequence doesn't have to converge, of course. It can just bounce them back and forth between two things and never converge. But we can always extract a convergent subsequence. And the limit, again, lives in our compact set. Okay, so let's try to prove this. I'm going to take the approach of proving the contrapositive of this, just not that different from doing a proof by contradiction, I guess. So for the proof, let's approach like this. Okay, so I have a statement of the form that if A is true, then B is true. Okay, so if T is compact and we have some sequence, that's my A, then there's a convergent subsequence, that's my B. And this is equivalent to saying if B is false, then A is false. Okay, it's not really different. It's not so different from doing proof by contradiction, right? We start with, these are the things we know are true. Then we assume, let's assume the opposite of what we want to prove. So we assume not B is true. true. We managed to prove that not A is true, and suddenly that doesn't jive with what we know to be true. Okay, so this is, doing this accomplishes proving this. So what are we trying to prove? Okay, so what I'm going to try to prove? Not B. Not B means I've come up with a sequence that just has no convergent subsequence. Any subsequence I look at doesn't have a limit. Okay, so let xn be a sequence in T, have no convergent subsequences. Okay, so I want to prove that if not B is true, if I start with not B, I get to not A. Not A is the statement that T is not compact. In other words, that T violates Heine-Borel. Okay, so then T is not compact. Or in other words, T violates Heine-Borel. I'll give you the picture version of the proof first. Can we agree that this sequence that has no convergent subsequence, this is not just a sequence that repeats a constant or that has a few values that it just cycles through, right? This is a sequence that has infinitely many different values in it, right? If it had finitely many different values to choose from, at least one of them would have to repeat infinitely often, and we'd get a convergent subsequence. So we're going to just note that. Okay, the sequence xn has infinitely many different terms. All right, so now let's draw the picture of this. Here's my big set T. And I have points in my sequence in here. Here's x1, here's x2, here's x3, here's x4, wherever they are. But they never accumulate anywhere, right? If they accumulated somewhere, we'd get a limit. So that means I expect that I should be able to draw a little ball around here, a little neighborhood around here that doesn't contain any other point in my set sequence, or even in this set, right? If it contains something else in the sequence, no matter how small I made this ball, well, all of a sudden this is a limit point. We know it's not a limit point, so I can do this. I can find a neighborhood that just has nothing in it. And I can do the same thing over here. And I can do the same thing over here, right? With each one of these things, I can build a little bubble around them that contains no other point. So what I'm going to do when I create my open cover, these are going to be important to my open cover, right? I'm going to have an open cover that it has to cover other points in there, but it's also going to include these little balls, of which there are infinitely many of them, and each of these infinitely many balls contains exactly one point in my sequence. Any subcover has to still keep these balls in it because we still have to cover all the points in my sequence, but there's infinitely many of them. So what I'm trying to show is there's no way to just reduce myself to finitely many of these and still cover my whole set. This is what the picture of what I want to do here. I want to first show that, yes, I can draw these little balls around here that don't contain anything else in them. And then secondly, I use them to build an open cover that is just inherently finite, and there's nothing I can do about this. draw these balls around here. I need to be able to draw a ball with a positive radius, not a zero radius, but something that is actually an open set. So my first lemma is just that I can draw these little open sets. So let X be a point in my set, and let's define epsilon X to be the radius of the ball I'm going to stick around each point. So what I'm also going to do here, I need to cover not just the points in my sequence, I need to cover the whole set. So I also need to cover this point Y here that's not in my sequence. And I want to make sure when I draw a ball around it that I'm not drawing a ball that might contain some of these other points in my sequence. Okay, so my first lemma is that yes, I can draw balls around the points in my sequence, but also I can draw balls around the other points that don't overlap with these little balls. I want to be forced to hold on to these infinitely many different balls. Okay, so I'm going to define epsilon X this way to be the infimum of the distance between xn and x over all xn in my sequence. Okay, so what is this doing? This is taking a generic point over here. Let me call it X to match what I wrote over there. Okay, this point is not necessarily in my sequence. It might be or it might not be, but it's just a generic point in my set. And what I'm saying is, well, let's look at the distance between this and x1. Let's look at the distance between this and x2. Let's look at the distance between this and all the points in my sequence. And then I'm going to take the infimum of all of those. Now I should have a ball that doesn't contain x1, doesn't contain x2, doesn't contain any of the points in my sequence. And as long as I haven't had to shrink my ball to 0 to do this, I've got an open set around here that isn't grabbing on to any points in my sequence. So then, not that, we gotta prove this. Then epsilon X is strictly positive. It doesn't decrease to 0. Well, this is going to work because we know that there's no possible way of choosing a subsequence of these points that converges to x, right? We're told there's no possible subsequence that converges to x. So nothing in here should accumulate near x. There should be a gap. X is not a limit point of this sequence. Okay, so let's do a little proof of this lemma here. And what I'm going to argue is that if this infimum was 0 instead of strictly positive, well, that would mean I'd have a subsequence that actually converges to x, which we know is not true. So suppose epsilon x equals 0. Okay, well, what does that mean? That means that no matter how small an epsilon I choose, I can make this arbitrarily small, right? I can always make that arbitrarily close to 0. So we know that for all epsilon greater than 0, there always exists some point in my sequence such that this can be made less than epsilon. Okay, so now I'm just going to start doing this for a sequence of epsilons. We'll do this for epsilon equals 1, do it for epsilon equals 1/2, 1/3, 1/4, right? And I'm going to get a sequence of points that converges to x here. Okay, so we can find some index, let's call it I1, such that we're within a distance 1. Okay, and then we keep going. We find I2 such that we're within a distance within a distance of a half, but also less than all the distances that come before us, because we want to make sure I2 is bigger than I1. So we can certainly specify that. Let's find I2 bigger than I1, which this is less than a half. Okay, and we can keep going. Let's find, in general, In bigger than In minus 1, such that we're within a distance of 1 over n. Well, now I've just built a subsequence. xi1, xi2, xi3, up to xin. That's just a subsequence of my original sequence. And we see that the distance between points in my subsequence and x is converging to 0. Okay, so xin is a subsequence. Okay, and we know that the limit as n goes to infinity of the distance between xin and x equals 0. And that's how we define convergence in a metric space. So we have indeed that the limit as n goes to infinity of xin equals x, which is a point in our metric space, right? And this is going to contradict the fact that we said there are no convergent subsequences. So we found a convergent subsequence. Okay, and this is a contradiction. So we got a contradiction, or what was our assumption? Our assumption was that epsilon x was equal to 0. That must be wrong. It must be the case that actually epsilon x is strictly positive. Of course, it's a distance. These are distances. It can never be negative. Okay, so what does that mean? That means, indeed, I can find a positive radius here, such that I draw the ball around here, and at most it reaches to one of these points, but it's not containing any of these points in its interior. And now that is how, yeah.
That should be greater than 0, right?
Thank you, that should be greater than 0. And this is how we're going to construct an open cover. So what was our goal here? Our goal was to say that, to prove that, or under these assumptions, T is not compact. Right, because we were doing this proof by contrapositive. So our goal was, let's prove T is not compact. That means we need to show there's a way of producing an open cover such that I just cannot abstract a finite subcover. Now this is how I'm going to create my open cover. I'm going to draw the balls around here, okay, with radius epsilon x. All of these balls will have different radii, potentially. This ball here has radius epsilon x1. Right, so each of these has a different radius, but they're all positive, which means these are all indeed open sets. And each of these open sets either is a singleton, right? Either contains exactly one point in my sequence, right, or no points in my sequence. Okay, so let's use this to construct an open cover. Okay, so what am I going to do? Again, I'm just going to define these little neighborhoods, and I'm going to do it for every point in my set T, right? If I do it for every point in my set T, then I know that everything in T is covered. And maybe things are covered more than once, I don't know, but certainly everything is covered. Okay, so let's define one open set, corresponding to each point. Okay, so I'm just going to define this as an open neighborhood. So this is going to be all the sets, all the points in my set that are within a distance epsilon x. Okay, so that's the picture I've drawn there. Okay, and I might have, here's my x. I might have another point y over here that might overlap with this, or it might even contain x, that's fine. But the key is it doesn't contain any of the other points in my sequence. That's what's important. The points in the sequence belong to exactly one of these sets. Okay, let's stay over here. Okay, so I pick a point in my sequence. Okay, then what do we know? We know that xn, belongs to, it belongs to the ball I've constructed around it, of course. But it doesn't belong to any of these other open sets, right? By design, we've made sure that none of these other radii are allowed to hit points in my sequence, right? So what's the smallest possible distance to anything in my sequence? That's our radius. So this ball contains x4, it can't contain any other point in the sequence. This ball contains maybe a bunch of points in the set, but it never is able to reach any of the points in my sequence. So if I look at any point in my sequence, it lives in this set, but it doesn't live in any of the others. Okay, now I say, well, these together form a nice open covering. Okay, this is certainly an open covering. Okay, it's quite possibly overkill, right? I've designed an open set for every single point in my set, so of course it's a covering. And they've all been designed to be open, right? This is precisely how we define an open neighborhood in a metric space. So this is certainly an open covering. And now I start saying, well, can I find a finite subcover of this? Well, any subcover must cover the infinitely many points in our sequence. Okay, so I can start throwing out sets, but I have to keep at least one set that contains x1. Well, actually there's only one set that contains x1. I have to keep at least one set that contains x2, but again, there's only one set that contains x2. So all I say, any subcover must include the sets. Well, the open set I built around x1, the open set I built around x2, and so on. Well, there's infinitely many of these. We said there's infinitely many different points in our sequence, so there's infinitely many of these, right? There may be a little bit of repetition, but there's not too much repetition. So what are we saying? Any subcover must be infinite. Okay, so there's no finite subcover. There's just no way of doing it. If we decide to look at any finite collection of these, we're going to be throwing out some of the points in our sequence. And we're not allowed to do that. A cover has to cover everything. Okay, so we conclude that, well, there is simply no finite subcover out there. So T doesn't satisfy the Heine-Borel property, T, which is how we define compactness. T is not compact. Questions? Yeah.
Let's say when we got half this sequence that does not converge, but the points stay close together, they can jump like this, it does not converge.
Okay, so the points jump around, but they don't converge, but you can still extract a finite, a convergent subsequence. Right, so if they stay close together, I mean, if we think in Rn, if we have infinitely many things that stay close together, right, we should be able to always extract a convergent subsequence. They might bounce around, but they have to accumulate somewhere.
That's only in Rn?
We'll put that in Rn, yeah. Is it true in a general metric space? So in Rn, I guess we showed this because we said, well, if things are closed and bounded, they have to accumulate somewhere. So I'm going to get in a few minutes to what about closed and bounded sets and see what the relationship is there. But yeah, certainly we can have things jump around in different ways. I mean, think of the example we do for R with the discrete metric. There's infinitely many of these things. They stay close together. They all stay close together in some sense because nothing is ever more than a distance 1 apart, right? But you could certainly imagine building non-convergent sequences. It's very easy to build non-convergent sequences in R in that metric. So let's state the theorem that we have here, just as a reminder. Our conclusion, we did the contrapositive here, but the conclusion we really care about is that if T is compact and Xn is any sequence, okay, then certainly Xn has a convergent subsequence. So things have to accumulate somewhere. This is actually an if and only if statement. So I've proved one direction here, but you can prove the other direction. If every sequence admits a convergent subsequence, then you're actually in a compact set. Okay, so you can look at your textbook for that, but that is another way of characterizing compactness. Okay, so this is actually an if and only if. Okay, so T is compact. if and only if every sequence has a convergent subsequence. So if you have to show if something is compact, this is Heine-Borel is how we defined it. This is an equivalent characterization. You could show that given any sequence, you can extract a convergent subsequence. That would prove compactness. Okay, so maybe to jump more to your question, what if I have a bunch of things that are close together? So let's go back to this example under the discrete metric. All right, we already saw this is closed and bounded. Okay, so in some sense, I take any sequence in here and the points in the sequence stay close together, right? Even if I take the sequence 1, 2, 3, 4, the counting numbers, they stay close together in this metric because nothing is ever more than a distance 1 apart from anything else. Is this a compact set? Okay, you're saying no. Why is it not compact?
I'm just kind of intuitively thinking about it, but yeah, I mean, I just don't think you can really put a finite subcovering.
You don't think you can do a finite subcovering of this? Yeah, your intuition is correct here, right? So, I mean, there's different ways to argue this. I could argue that we violate Heine-Borel. I could argue that I can find sequences that don't have a convergent subsequence. But yeah, so for example, let's take this covering. Let's let Hx be the set of all points that are, say, a distance within a distance 1 but not equal to 1. And what is this set equal to? Yeah. Just the point x. This is a singleton, right? We've played games with this discrete metric before, and we've seen that actually singletons themselves are open sets in this metric. So I could create a cover like this. The set of all of these hx's. And this is an open covering. Right? Another example where I have one ball around each point. Every point is covered, so this is an open covering. But in this metric, I can't take a finite subcover. I can't get rid of any of these sets. They're all necessary because each of the sets in here is a singleton. Okay, there is no finite subcover. I can't throw out any of these sets. I can't even throw out one of these sets. Right, because each point is contained in only one of these hx's. Okay, so this is an example that violates Heine-Borel. This is not compact as we've defined it. So even though things stay close together in some sense, we have a bounded set and it's also closed. It's not the same as compactness anymore the way we've defined it. So In Rn, we get lucky, we have this really easy way of characterizing compactness, closed and bounded. That's not true in general, so we got lucky with that in Rn, but it's not true for general metric spaces that Heine-Borel is equivalent to closed and bounded. So I could choose to define compactness as closed and bounded. You can define things how you want to define them. The problem with that is it's not that useful to me, right? Because my real motivation for studying compactness was I want to be able to talk about convergent sequences. Closed and bounded doesn't let me do that anymore. And this is an example where I could easily build a sequence in this metric space that just doesn't have a convergent sequence. The one we talked about, the counting numbers, I take the sequence 1, 2, 3, 4, and that doesn't converge, even though my set is closed and bounded. So this example is not compact. And here we see that actually Heine-Borel is not equivalent to closed and bounded. So when we define compactness, we've got to pick one or the other. I'm picking Heine-Borel because it lets me do things that are interesting to me. Now the idea here will be, all right, Heine-Borel is our new definition of compactness. Now you give me the metric space that you're really interested in. Maybe it's Euclidean space, maybe it's Rn with the Euclidean metric. Now I try to use the concrete information that you've given me about the metric space you care about to come up with some easier tests for compactness. So in Rn with the Euclidean metric, we studied a bit and we say actually in this particular metric space, closed and bounded is equivalent to compactness. That's an easier test. Now next class we're going to do the same thing with the continuous functions on a closed bounded interval. We're going to say we're interested in compactness because we'd like to know about sequences that converge to a continuous limit. So we want to know how to check if something is compact. Checking Heine-Borel is kind of a pain. So is there something easier, given this specific metric space that we care about, is there an easier way to test for compactness? Well, closed and bounded isn't going to be the answer there, but we'll be able to find another set of criteria that is very easy to check, specific to the particular metric space, but lets us easily check without dealing with subcovers. Yes, this is a compact set. Now we can have confidence that we're getting limits to our sequences. Okay, so that's the game. We started with a special case of Rn and started with an easy test. But the easy test is not really the true definition. It's just the easy test for that particular metric space. So our goal is going to be, all right, you give me your metric space. Now we try to come up with an easy test. Do the work once of showing that's equivalent to this Heine-Borel property, and then never think about Heine-Borel again when we're playing with this metric space. Okay, so we'll make this note. Heine-Borel is certainly not equivalent to being closed and bounded. In general. Okay, so our goal is going to be, given the metric space we care about, let's find easier tests for compactness. Okay, now that will be a problem for next class. We're going to do a few more general things today. So that we have, and these are tools that are still available to us next class if they're general. One corollary of this result is that Cauchy sequences converge. This was some of our motivation. I mean, we talked about complete spaces, and we want easy tests for convergence. This is really our motivation for doing this. I have a sequence that I've generated somehow, probably through some iterative procedure. I want to know, does it converge? All right, so far, I have a way to check if it has a convergent subsequence. But at the end of the day, I want to run my sequence. and eventually I want to stop, and I would like to know that I've landed close to the limit I'm hoping for. Not that my sequence is bouncing around, and some of the points are close to the limit and some are not, and I don't know where I stopped. So the important corollary of this result is that Cauchy sequences converge. So if T is compact, okay, and we have is a Cauchy sequence. Okay, then Tn converges to a limit in my set. Okay, we've done most of the work of proving this already. So what's the approach? Well, we start with this sequence. We say, oh, I'd like to know this sequence converges. I don't. But I know there's a convergent subsequence. We already did that work. We showed that. So, okay, I've got a subsequence that converges. But at the same time, things in this sequence are going to stay really close to things in my subsequence, right? That's the Cauchy property. Okay, so we're going to be able to use that to say a subsequence converges, everything else eventually stays really close to things in the subsequence. So actually, yeah, the whole thing converges. Okay, so the proof is we know by compactness there exists a convergent subsequence. Okay, so we pick our epsilon, and I'm just going to write down these two facts. That thing has a limit, and that this object is Cauchy. So, all right, both of these facts give me an n star. I'm going to pick whatever is the biggest of those two n stars. I'm going to pick an n star that works for both facts. So we know there exists n stars such that, okay, if n is bigger than n star, then the distance between Tn, let's call it Nj. If Nj is bigger than n star, then Tnj and T is less than epsilon. Right, that's the statement that this subsequence converges to a limit. Okay, and if n and m are bigger than n star, then the distance between Tn and Tm is also less than epsilon. Okay, so let's put this together. Let's let n be bigger than n star. So I would like to show that this holds, but without the subscript, right? Not just that the points in my subsequence satisfy this, but everything satisfies this. Okay, so now I have something not in my subsequence, but I want to show that actually it gets close to the limit. Okay, how am I going to do that? I'm going to compare it to something that is in my subsequence. Okay, so let's let let's call it m sub j be bigger than n star. So that's the guy I'm going to compare it to. Okay, and what I want is to show that this is small. The distance between Tn and T is small, so that general points in my original sequence converge. All right, what's my tool here? How do I bring in this point? Yeah. triangle inequality. Was always our favorite tool for doing these things. So this is less than or equal to the distance between Tn and Tmj plus the distance from Tmj to T. Well, these subscripts are both bigger than n star. Okay, so we know this is less than epsilon. This is a point in our subsequence, which is, again, beyond n star. So we know this is less than epsilon. So indeed, if I take a generic point in my sequence, as long as I'm far enough down my sequence, I can always find an n star such that this can be made arbitrarily small. So this is indeed the statement that my original sequence converges. So Cauchy sequences converge. This is the big result that we've been hoping for some time. We started worrying about this before the midterm, but we'd like to be able to have an easy test for convergence. Now we have the Cauchy test, as long as we're in a compact space. All right. We still need to know how to check if a set is compact. In Rn, with the Euclidean metric, we know how to do that. In other metric spaces, we'll have to design tests that are suitable. But we're starting to have some tools now for proving convergence. Now, one other thing that is true about compact sets which we can use in general. Compact sets are closed and bounded. That is true. This is not an if and only if, but if I have a compact set, it's automatically closed and bounded. Okay, so if I'm playing with a compact set, I can use the properties. I can assume closed and bounded. I can't use closed and bounded to prove something is compact, but this direction works. Right, and in Euclidean space we got lucky. It was an if and only if. Okay, so there's two things to show, that T is closed and that T is bounded. Okay, so let's show that T is closed. We're going to argue that T contains all of its limit points. That's one way of characterizing a closed set. Okay, so let's let T be any limit point. Okay, so, all right, here's T. Here we found the limit point. That means that things are trying to accumulate here, right? So from here, we're going to be able to build a sequence that seems to converge to T. The question is this actually in our set? Well, if we have a sequence that converges somewhere, we're going to be able to argue, actually, well, it's a Cauchy sequence then. And if it's a Cauchy sequence, then we know actually its limit stays in our original set. Okay, so we can build a neighborhood. Right? Every neighborhood contains some point in capital T. So we can say that for all n, we can find some point that's within a distance 1 over n of my limit point. Right? That's what it means for something to be a limit point. Points get arbitrarily close to here. All right, so that's the statement that Tn converges to T. And we've showed before, convergent sequences are always Cauchy sequences. Cauchy implies converging into something in my set is a different question. But convergent sequences are always Cauchy sequences. And what we just argued via compactness is great, Cauchy sequences actually do converge and the limit stays in our set. Right, that's what compactness buys us. So, since T of compact the limit T of a Cauchy sequence is in our original set. So we've got a closed set. Okay, so these are the general property of compact sets. Compact sets are always closed. So again, we can use that. Whatever metric space we have to be in, if we happen to know we have a compact set, we can use that as closed. Okay, bounded is the other question to answer. Okay, here's how I'm going to approach this one. I'm going to, I need to pick 2 points in here and show that, you know, there's a bound to how far apart they can be. I'm going to start by building an open covering of this set. Any open covering will do. I'm going to take a particular open covering where I just build balls of radius 1 around every point. Okay, it's overkill, right? Probably. So I'm just going to start building lots and lots and lots and lots of balls of radius 1. There's too many of them. Okay, so let's cover in many balls of radius 1. Okay, so H is going to be, my open covering, is going to be the collection of all balls of radius 1 about every point in the set. Okay, so again, overkill. I've stuck an open set around every point. There might be a lot of these. But now, what's the key here? The key here is we're in a compact set, so this definitely is overkill. Right? When I did this for R under the discrete metric, it felt like overkill, but actually we needed all of those infinitely many sets. Here, that's not true. There's too many of them. I know that finitely many of them is good enough. Okay? So we know, so this is an open covering, but since T is compact, all right, there exists a finite set. Let's say, call it this. That also covers T. Okay, so I go back to my set T, and now, really there's just finitely many of these that I need. I'm going to get rid of most of them. Okay, so there's some number of these, but it's finite. So I've called it K here. There's K balls left in this open covering. So now I pick a point U, and I pick a point V that lies somewhere in here, and I each find one of these balls. And the key here now is to get from U to V to find the distance between them. Well, at most I have to walk across these K balls, right? And there's finitely many of them. I don't have to run across infinitely many of these. I just need to know distance from this ball to this ball, this ball to this ball. I don't know the path I'm taking, but there's finitely many of these things that I have to walk through here. Okay, so if we write that out precisely, given any U and V, what do we know? We know that, well, this is a finite self-cover, so U belongs to one of these balls, right? U's and T have to live in one of these open sets in the cover. Similarly for V, okay, so U belongs to one of these, V belongs to one of these, okay, for some value of these. Okay, so what's the distance between U and V? Well, I'll start by going from U to the center of its ball. Then I'll go from the center of this ball to the center of this ball. And then from the center of this ball to V. So this is going to be at most, okay, the distance from U to TM, the distance from TM to TN, and then the distance from TN to V. These 2 points live within a ball of radius 1 with TM being the center. So this distance is less than 1. This distance similarly is less than 1. This distance, I don't really know what it is because I have no idea whether I pick balls that are next to each other or spread as far apart as possible. So the best I can say is that this is going to be bounded by the maximum possible distance between the center of any two balls. But there's finitely many of these, right? I'm taking the maximum of finitely many values. So this is going to be finite, right? The distance between T1 and T2 is some finite number. I don't know what it is, but it's some number. The distance between T1 and T8 is, again, some finite number. This is the maximum of a whole bunch of finite things. It's a maximum of finitely many finite things. So this is a maximum of finitely many real numbers. Okay, so there's no way it can be infinite. This stays finite.
Did you also say it's less than like the max term? Did you say it's less than K?
You could probably do some argument that it's less than K or 2K or something like that. You just have to walk across carefully.
Okay.
It's not important what bound I get here, it's just that it is a bound. So yeah. So in general, all right, if this is true no matter what U and V are, well, then the diameter is certainly less than 2 plus whatever this maximum was. So indeed, my set is bounded. Okay, so this is something we can use. If I have a compact set, it's bounded. So if I want to take 2 points between them, I know they can't run too far apart. All right, that can be useful, and that's something we can carry forward into talking about continuous functions, for example. Similarly, we can take forward this property of being closed when we're talking about continuous functions, as long as we know we have a compact set. Okay, so again, Not an if and only if, but this does give us some extra properties of compact sets. All right, and then next class, again, we'll start talking about specifics of continuous functions and try to do some more realistic looking examples.